Thanks for coming. We have a much better audience, much bigger audience than last time, so I guess you all saw the announcement. Anyway, today we have Raja Affandi. Do you use your middle name? No. Okay, Raja Affandi, and he's going to talk about determinantal point processes and large-scale inference.
Good afternoon. It's good to be back. I did my undergrad and master's here, so it really feels good to be back. So I'm interested in point processes. I think they're very interesting in more ways than just spatial statistics. And today I'm going to talk about a very specific class of repulsive point process called determinantal point process. And it's joint work with Emily Fox, Ben Taskar, and Alex Kulesza. So I'm going to talk about DPPs, which is short form of determinantal point processes. But there are a few key themes that I want to highlight for point processing in general. So let's start with the history of DPPs. In the 1970s, basically a bunch of people in physics and mathematics was interested in modeling atoms. And so the whole idea is that the most common things to use is a uniform random sampling, or equivalently the Poisson process. But the problem with Poisson process is that if you were to randomly select them, you're going to have a bunch of clusters, which is not a suitable model for the kind of repulsive atoms that people are looking at. So in 1975, there was a paper that actually lays the foundation of a DPP, where as a process, you can see that it's more repulsive. It's more well-suited for the kind of application in quantum physics they were looking at. So it was a nice theory, and I'll show you later some of the nice properties of DPP. But the question that I'm interested in is kind of like the key idea of how do you do efficient large-scale inference and learning on these processes, right? So before I get to that, you might ask, why point processes, The key idea is that when I talk about point processes, I'm talking more beyond the spatial statistics, where usually these point processes are applied. To give you an example, here's one of the applications we looked at in my paper. So this is the data from mocap, motion capture, where there's a video of someone playing basketball. And you can think of the frames of this video as being a particular item. And you can extract features from them. And if you consider the high dimensional feature as some sort of location of these items in a high dimension, in this case, I think it's 62 dimension space, you can think of it as a point process. And one of the applications we looked at is from that collection of thousands of frames, how do we select a representative set of 10 or 12 frames that could help people summarize the activity, right? And I'll go into the detail later and how we do that. But the whole idea is that we're having this paradigm shift of point processes beyond just spatial statistics into machine learning regime. And another key idea that I want to highlight is point processor as part of the inference tool. So usually, the connection people make between point processor and inference tools is, oh, you're given a point process, how do you learn or how do you infer point processes, right? So I'm going to take this and turn it on its head and say that, what if we use point processes to facilitate learning or any algorithm you can think of that suits a particular problem? Graphical model, MCMC type algorithms. For example, in one of my paper, we look at DPPs as a diversity prior, right? So a mixture of Gaussians, and I'll talk about it in more detail later. But the whole idea is that you have a mixture of Gaussian, right? So you have an underlying mixture of Gaussian, and you want to learn the mixture of Gaussian using your standard Gibbs MCMC type algorithm. The whole idea is that if you just consider using an IID prior, like what usually people do, you're going to end up with a lot of overlapping clusters. So the whole idea is that can you use a repulsive point process like a DPP to get a more interpretable cluster? Again, I'll talk in detail later, but the whole idea is that I want to highlight the fact that using point processes is part of inference tools. Right? So the outline for this, I'm first going to talk about the background of discrete DPPs. Then I'm going to talk about my work on the large-scale nonlinear DPPs and how we extend this to continuous setting. And I'm going to talk about, if I have time, about learning, especially large-scale learning, and how we would extend this to a temporal extension for the DPP. Right? So let's go back to the background. So, like I said, DPP has been around since the 1970s, but people don't really give it much thought until 2005 and later, when people see the application for DPP in discrete case as being something relevant to machine learning. So let me start off by giving a motivation of why DPP is useful. This is something that you know, an example that everybody can relate to. You want to go do image search on Google, right? And the whole idea is that, let's say you search for the word cardinals. Right? This was a couple of years back ago. I actually did this and look at top results from Google. So the first 3 results is a bunch of sports teams. Well, it is nice if you're actually looking for the sports team, but what ideally you want to get is kind of like a more diverse sets of results that kind of like encompass the word cardinals, right? So this is where DPP is useful, right? And how do you do this? So the whole idea of DPP is that you have, in the discrete case, you have a bunch of items in your base set. So you have n such items. So you can imagine the colors being the kind of similarity measure between the items. And the whole idea is that you can do, in ON cube, you can get a diverse subset from that. Right? So just like you do the image search, you have thousands of images. How do you do a selection of like 10 most relevant and diverse collection of images, right? So let's consider why this is actually quite impressive, right? So how would you naively do this? You would take your collection of items, and you would give probability to every single sub-collection of the items. Example here. So what's the problem with this? You need 2 to the n of such assignment. And so your probability distribution grows exponentially as a function of the number of base items you have, right? So just simply rephrasing the subset selection as a point process is not enough. This is where DPP comes in. So the whole idea of DPP is, so you have a bunch of items, and you want to define a kernel where the element Lij of your matrix is some sort of a similarity difference between the items, right? So you have an n by n. And the whole idea is that if you want to ask a question, what is a probability of selecting a set Y, highlighted here, all you need to do is look at the submatrix that contains the element of Y, and then the probability distribution is given by the determinant of that submatrix, right? So parameterizing the kernel like this is pretty nice. And how do you get such kernel? Here's one example, which typically people use in image search and text corpus and things like that. You can look at just looking at feature vectors of the items, in this case the images, and then you want to look at the dot product. Then you can build the matrix as just basically the dot product of the items, right? That's one way of getting the kernel out of that. So why is DPP a repulsive point process? Why does it have that diversity component to it? Well, the whole idea is that, remember that the determinant of a particular matrix is the volume squared of the space spanned by the entries of the matrix. So for example, in our example, we have two cases that are quite similar. They're both sports team. And then if you look at the feature vectors, the dot product of them, and compare it with the basically the probability of choosing two other items, which is more diverse, then basically the determinant is going to give you the square of the volume spanned by those items, right? So you can imagine. So the nice thing about the DPP, you're not only looking at pairwise volume. You're looking at simultaneously choosing n items. So in a case where you choose 10 items, you can imagine the picture would be like a 10-dimensional volume that you're spanning, and then you're asked what's the volume spanned by those feature vectors. So as you can see in this example, choosing something that's more diverse gives you a higher probability under the DPP. So that's why generating from a DPP gives you a diverse set of items. So why DPPs, right? There are very nice mathematical formulas that you can derive out of DPPs. Something you've seen just now, like normalization can be formed in a closed form. So if you sum all possible set y, then this normalization constant will come up. So it's pretty nice. You can consider marginal. What is the probability of choosing a particular item? What is the probability of a particular item is in a particular set? You can phrase that. But what I think is very interesting is the conditioning. So you're asking, given that I've already chosen a particular set to be included in my collection, what is the probability of choosing some other set? And it's also a DPP, right? So it has all this nice mathematical formality to it. And here's another one, which I think like the reason why DPP became famous is because of the sampling algorithm. This was discovered by Hafiz in 2006. So the whole idea is that how do you sample from a DPP, right? The way you do it is you look at the kernel matrix, you do the eigen decomposition. So let's say that's your eigen decomposition of 6 items, right? And you do it in 2 phases. The first phase, you want to select the eigenvectors according to a Bernoulli distribution based on the eigenvalues, right? So let's say that those are 3 eigenvectors that you happen to sample from. And in the second phase, what you do is you want to sample a particular item based on the projection of that item on the eigenvector, right? So you do the projection of the eigenvector, and then you do Gram-Schmidt orthogonalization. So the nice thing about this is this requires O(n) cubed for the eigen decomposition. This requires O(n) k squared, where k is the number of points that you're choosing. So it's a pretty efficient algorithm, right? So in picture, I don't know if you can see this, but the whole idea is that you can represent it here, that here's your probability distribution of selecting the items. You choose one item, and then you do the Gram-Schmidt orthogonalization. And so basically, you keep doing that, and you see the area around the point is has low probability of being chosen, right? So that's basically the background of the DPP. But in this day and age, getting a nice sampling algorithm and getting a nice inference method is not enough. We want to consider large scale. When we're talking about tens of thousands, hundreds of thousands, millions of data set, that was what my work was interested in doing large scale DPPs. Because, so it's based on our paper AI stats. So the whole idea is that, back to the idea of the video summarization. So, all these different videos, I want to summarize what we're doing. So here, I want to select a representative frame that's in that video. In this case, once I get this, then it's easier for me to summarize what that activity is. Same thing with the other one, basketball, dancing. The problem here is that it is still true that we need O(n) cubed to get the sample, but in this case, even in the motion capture data we have, actually from CMU, we have like 24,000 such frames, and even in this case, like the DPP would probably going to be really slow, or possibly choke at this point, right? So consider a 24,000 by 24,000 matrix, doing the eigendecomposition and so on. So the question that I was trying to answer, like, how do we do this sampling, right? So the first question we want to ask, this problem has been solved in the case where the kernel is represented by the dot product, the inner product of the feature vectors, like the example we have with the images just now. It was done in 2010 by Kulesza and Taskar. So the whole idea is that it's kind of cute. The whole idea is that if there's like a d-dimensional feature vector that for each item there's d-dimensional feature vector, and you have L, which is n by n, and n is much bigger than d, we know the rank of L is going to be d, right? So instead of sampling from L, what you can do is do what's called a dual sampling. So instead of taking the inner product, I'm taking the outer product. That's going to end me up with a smaller d by d matrix C, and from then I can do the eigendecomposition on C and then do the sampling, right? So this has been done in 2010. It's pretty nice, but the idea is, what if you don't have such a structure, right? So, for example, I'm going to give you a standard example of what we do in DPP, which is the RBF kernel, right? So it's just Gaussian RBF kernel. The whole idea with the RBF kernel is that if you were to represent the RBF kernel as inner product of feature vectors, you would need infinite number of features to do that, right? So now, what we have before of having small dimension and doing the dual no longer applies, because now our D is infinite. So how do we do a sampling? So the idea is we want to do a low rank approximation, and the whole idea is that now still consider the case where we want to take we want to represent the kernel as a dot product kernel. Now we have an infinite number of features. What you can do is do a low rank approximation on the features. That will get us back to the problem we had before, where now our number of features is some d, right? So that's our approximation. Then we can do the same dual decomposition like we did with the we did before. And one way that we can do that is Nystrom approximation. Right? So I mean, there are questions why we do a Nystrom approximation. I won't go into the details comparing this with the other methods, but the idea of the Nystrom approximation is that if I consider here is the space spanned by all the items, right? The question is, how can I recover these in space? Right? So that's the basic question of like doing a low rank kernel approximation, right? You can use spectral method, right? So that's probably the best way of doing it in terms of result. That's the best way. You do SVD and things like that. That will give you basically the best rank D matrix. But in order to use spectral method, you need O(n) cube as well. So that doesn't help our cause of simplifying the problem, right? So instead, we do what's called a Nystrom approximation, where instead of choosing like the eigenvector, eigenvalue that best represent, we just choose the items themselves that serves as landmarks, right? So for example, if you want the distance between 2 points, right? You want to know the element. What you can do is that you can basically like infer it from the the distance between point A to all the landmarks and point B to all the landmarks, and kind of like reconstruct the distance between point A and point B. So let me go into more a formal definition of what a Nystrom approximation is. So I start with matrix L, and then I consider that I'm going to rearrange it so that my landmarks are the first D component of the matrix. So then I'm going to decompose our matrix as here's a submatrix containing all the landmarks, and then here's the column vector and the row vector associated with the landmarks. What the Nystrom approximation does is that you take the inverse of that submatrix, and then you multiply with the column and row. That will give you an approximation of the matrix, the original matrix. Right? This has been studied a lot. There's a lot of papers out there. I'm just going to highlight, I won't go into detail, but just the point of this slide is to show that there are well-established results for Nystrom approximation out there. You can do uniform sampling where you choose the landmark randomly, or you can do stochastic sampling where you choose one at a time iteratively in a more intelligent fashion. But the results are out there, and notice that all these results are in terms of the matrix norms. But the question that we're trying to ask, although we have a good bound on the spectral norm error, how does it translate to the DPP approximation itself? Right? So one such measure that we consider is variation distance, which is simply the difference between the probability distribution between the original DPP and the DPP with the approximated kernel, right? And the problem with that is that, we not only have error in terms of the L2 norm, we have error in terms of the determinants of each possible subset. So it's not clear how this error in the matrix norm will propagate to the error in the variation distance. So that was the question we want to ask. To give you an example why this is a huge problem, here's a very simple toy example. Here's a matrix with diagonal with a large value m and epsilon in the last diagonal entry. So let's say that's going to be our approximation of L tilde, right? And this is the best you can do, right? You preserve all the big values on the diagonal and approximate that epsilon with 0 here. So this will give you a rank that's one smaller than this, right? That's the best you can do in terms of the norm error, which is epsilon. But the problem is, if you look at a particular submatrix and you take the determinant of that, so the determinant is just going to be the product of the diagonal, that error can really be big, right? Depending on the value of m. So that's the kind of worry we have, So in the paper, we came out with a set-wise bounds on DPP, right? Where we concluded that the norm 2 error plays a big role, indeed. And basically, so the bounds are tight. In the case we had before, the bounds are tight here. That's the best we can do. So the nice thing is that we run this against a few data sets. And here is what we get just by looking at our bounds. And here's what we get by looking at the empirical value. So as you can see that, the theory tracks the behavior of the empirical performance of the different types of Nystrom approximation really well. Here's a better example. So in this example, in this particular abalone data set, it's found that theoretically that using an adaptive version of the Nystrom outperforms the uniform. by a lot. And empirically, that's the case as well. So we achieve our goal of having the bounds and having it give a clue of what methods to use, what type of landmark selection to use. And we apply it in our motion capture summarization. So we use RBF kernel. So in this case, we simplify the problem by just looking at 9-dimensional space, where 9-dimensional corresponds to the different sensors, different location of the body. And we compare it with random sampling. So the whole idea of the experiment is to see if we do a Nystrom approximate DPP, does it give us the same kind of diversity that that we would expect, right? We ran this on a user survey, and we asked people randomly. We chose one set from Nystrom approximate DPP and another set from random sampling, and we asked them basically which frames are more diverse, which is a better representation for the activity, and which frames are more characteristic. And the result was pretty astounding, that indeed we were able to conclude that our Nystrom approximate DPP does give us more diverse representation of the frames, right? So the takeaway message here is that large-scale inference can be done on the DPP, and it works really well in practice. So that's kind of like a takeaway message from that paper, that we pretty much kind of like fill in that that question mark we had before by using the Nystrom. We can also do a random kitchen sink. I won't go into that because we don't have much time, but in general, we seem to prefer Nystrom over the other methods. So the whole idea is that now, instead of dealing with a large set of base items, discrete base items, what if we consider continuous space, right? So that's our paper in NIPS. So the whole idea is now, instead of looking at n items and choosing a sub-collection from the item, we want to look at probability of specific point configuration from that space, right? So now the problem is we're going from an n by n matrix to a kernel operator, right? And we define the DPP on this continuous space as simply the proportion of the determinant of that specific point configuration. So it's still the same idea that if points are very close by, they span a small volume, so the probability is low. And if the points are more spread out, they span a larger volume, and so the probability of choosing that point is higher in DPP. So the problem with continuous, this is kind of a funny thing, because DPP in the 70s was defined for continuous spaces, right? It was well defined, but nobody knows how to sample from them. And the reason why it's so hard to sample from them is like going from eigendecomposition of a matrix to eigendecomposition of an operator presents quite a challenge, because first of all, we might not know what the eigendecomposition